The next example is the electric potential from a circular plate. Okay. From a charge uniformly distributed on a circular plate. Okay. If we have a circular plate like this, and or the circular disc, and if we want to calculate potential at this point P, which is at a distance x from the center of the disc, from the center of the disc, and along the axis of the disc. Okay, and if we have the charge Q distribute uniformly on this disc, okay, and if the disc has the radius r. Okay, now how can we how can we get the value of V here? You may say that we divided this into a large number of very small pieces and calculate the electric potential from each piece, and then sum the total electric potential. Okay, but we have the better method, because from last example we know that we know the electric potential from a thin ring. Okay, so it means that if we divide the disc into a large number of thin rings, okay, and then we calculate the electric potential from each ring, dV, and then we sum up the ring from the smallest at the center and sum all the ring. So if we add up the potential from every ring, okay, so we have the total electric potential is equal to the sum of the electric potential from each ring. Okay, and from the previous example we know that if we look at this thin ring, and if the charge on this thin ring is dq, we know that the electric potential from this thin ring is equal to the dV is equal to the k dq over r square plus x square root. Okay, here r is the radius of this ring, so this is r. Okay, r is the radius of this ring, so we have dV equal to this expression. Now if we want to calculate the total electric potential, we put this dV into this equation and perform the integral. But to do that we need a further calculation, that is, if we write down the charge surface charge density on this disk. The surface charge density is equal, sigma is equal to Q over pi r square. Okay, sigma is equal to Q over pi r square, where r is the radius of the disk, so pi r square is the area of the disk, and Q is the total charge on the disk. It means that the charge on this ring EQ is equal to the sigma dA. So the potential, electric potential from this ring is K sigma dA over square root of r square plus x square. Here dA is the area, of this ring. Okay, and since we assume a thin ring, so we have that dA is equal to 2 pi r dr. So dV is equal to K sigma 2 pi r dr over the square root of r square plus x square. Okay, here dr is the thickness of the ring, of this ring. This is dr. Okay. Now we are ready to perform the integration. Okay, we have that V is the integral. The limit of integration is r equal to 0 to r equal to big R. That is, we start from the center of the disk and go, the upper limit is when the ring is at the outer limb of the disk with the radius big R. Okay, the integration of K sigma 2 pi r dr over r square plus x square. Okay, and you can see that K 2 pi are the constant. Sigma is also the constant because in this case we assume the uniform charge distribution. Uniform charge distribution. It means that sigma is a constant everywhere on the disk. So from that we can take K sigma and 2 pi out of the integration. So we have K sigma 2 pi integral from 0 to r of r dr over r square plus x square. Okay, like this. And the integral here is quite simple because we can use the method of, we can change the variable in the sense that if we use u equal to r square, so you can see that du is equal to 2R dr, or R dr is equal to half of du. So you can see that this is du. This is a half of du, and this is u. Okay. X is a constant because it's a distance from the center of the disk to point P that we want to calculate the electric potential. So we can do further by using the fact that du plus a constant is equal to du. So if we put c x squared as c, we can write r dr is equal to the half of du plus c. Okay. The detail of the calculation from this point is left for your do it yourself. Anyway, we can conclude that doing this integral, we will get the result that v is equal to the 2 pi k epsilon times r square plus x square square root of r square plus x square minus x. Okay, so this is the expression of the electric potential from a disk. Okay, you can see that the calculation is quite it's not so difficult because we perform the integration of the scalar function, not vector. If you compare with the calculation of the electric field from the disk, it's a little bit complicated, more complicated than this calculation. From this is the advantage of calculating the electric potential, because from the electric potential we can calculate the electric field. Okay, in this example and the previous example, we start from the electric field because we use the Coulomb's law in the calculation of the electric potential. But if we know the electric potential, we can calculate the electric field, and we will look at that. We will look at that calculation in the next slide.